So welcome back to the course. So yeah, we had this nice interlude, right, about Tagore, and talking about another inspirational figure from India. You probably know very well the person this complex is entitled to, right? Srinivasa Ramanujan. I probably mispronounced it, but he is a very famous mathematician, right? That came from India, and he made a big impact actually in mathematics worldwide, starting again from very disadvantageous conditions and not really a proper, scientific education. That's kind of really spark of genius, right? That kind of, unfortunately, actually died young. So it was really like one of these, mavericks, if you want, like these, like sparks, of brightness and genius that illuminate us now and then. And one thing actually I remember from what he said is like he didn't claim any merit about his discoveries because he actually claimed they came from God. So that's another story of humility, right? So, and I think that's probably the right approach to science and all we do, and the service in the different ways we do to community, right? As teachers, researchers, soldiers, and and any other job we undertake. I think we should keep in mind that it's bigger than us. The story is bigger than our CV. Bigger than our accolades, and in the end, it would be a very cheap, way to go about things if you just thought about yourself and what you can achieve for your own small circle of interest. So you should think bigger. Okay, I think you should think with in the end, accolades come as a byproduct of what you do. I don't think anybody that's set out to become the big guy will become the big guy. It doesn't work like that, in my opinion. So you actually have to do your work day in, day out, worrying very little about what the final goal is. You just have to do your best. Okay, really do not spare any energy and do your best. And that will lead to actually good results. But the funny thing is like a paradox. When you care so much about the outcome, you don't get it. On the other hand, if you have a very cool approach, you get the outcome, but you don't care anymore. So you see, it's more about the science and the work. You have to have this sacred blaze of science, and betterment of knowledge, and providing a better, understanding of the world around us and a better world to live in. That's what an engineer and a scientist should be about. It's not about collecting degrees, prizes, and so on. I don't think that's the way to go about it. Okay, so I hope that's not the way you go about things. Okay, so we go back to the course. So yesterday we introduced like the collocated MIMO, right, where you have all the antennas in one place, be it the base station or the mobile phone. Nowadays we kind of relax this assumption and we start to see what happens if you distribute antennas in a certain area, but you still want to have them kind of working together as a multi-antenna array. Okay, so it's a different deployment strategy. So where is MIMO headed? Now MIMO has been there for a while. Okay, definitely we have MIMO since the earlier generations. It was already quite much, in the agenda for 3G, definitely 4G, and 5G is no exception. It has evolved since the beginning. Okay, so in terms of basically the location of the antennas, which now do not have to be in the same place. So you have all of this work on coordinated MIMO. Sometimes you hear about coordinated multipoint, network MIMO, cooperative MIMO. They are all kind of, virtual MIMO. They're all kind of talking about the same concept, so to speak. So you do have antennas that are located at different places, possibly kilometers far apart, but yet they act as one array. So you do gain something in terms of diversity of the multipath environment, right? Because you are definitely going to experience very different channels, which, as we understood yesterday, is generally a good thing for MIMO. It's also a way to cope with interference in a smart way. So a big problem in cellular networks is that you have you transmit to your users, but so do the other base stations. And normally that's a bad thing because you interfere if you use the same frequency and you are in spatial proximity. But what if you actually ally to the interferer instead of fighting it, right? So in that case, you turn the interference from foe to friend, and that's what they try to do with these techniques. Okay, so instead of fighting the other, you just coordinate, and for example, you help each other serving users, or at least you make sure you don't disturb each other, you coordinate, right? So if we transmit to a user and that user is close to a user you are transmitting to, then maybe we should just coordinate and, you know, multiplex our transmissions somehow, maybe in time or, right, frequency and so on. Now, massive MIMO is about it's about the multi-user story of MIMO. So you have one base station, many mobile phones, a few at least, and you have a lot of antennas at the base station. Normally, the rule of thumb is at least one order of magnitude higher than the number of users. So the usual assumption in massive MIMO, we are going back to massive MIMO, but it's like you have one antenna per mobile phone, which is a good thing because as we discussed yesterday, the MIMO where you assume more antennas at the mobile phone didn't really fly because it's kind of complex, right? And it costs money, it drains energy, and we want to keep things as simple as possible on the user side. So massive MIMO, in fact, is a better deal in that sense, and it made it to the standard, for example, much quicker than waveforms for this very reason. Okay, it's not that waveforms are not good, and there is, I mean, we are going to talk about it in another paper club. It's a great, you know, set of, there is a great set of works and so on. It's just that there is this problem, okay, that you need to change the mobile phones, and that kind of slowed a bit the adoption of the standard. That wasn't the case with massive MIMO because you just have to upgrade base stations, and massive doesn't need to be thousands antennas. Okay, it could be, let's say, if you're serving 10 users, maybe sometimes with something like 50 antennas, you're good. Okay, and so you have to go, maybe nowadays you have something like in the order of 8 to 16. Some base stations have that. So it's not a huge upgrade, and you have space normally on the mast. You don't have a power issue because you're cabled, right? So, and you have only a few base stations as compared to the users. Okay, you control all of it. You're the operator, so it's an easier thing to change than the phones. The last development in MIMO has been due to the fact that we are moving up in frequency to basically, you know, in this ever-going quest for spectrum. Okay, the newcomer is millimeter wave spectrum, and for that you actually need to play with MIMO because the environment is very erratic, so it changes quite a lot. It's very sensitive to obstacles and, you know, and really attenuations. If the waves bounce off the walls, they kind of die. So you actually have to be very precise when you transmit. That's where beamforming helps, and precise to the point that you have to come up with what they call pencil beams, so very narrow beams. And for that, MIMO again is the solution, possibly massive MIMO. Okay, because the more antennas you have, the more precise you can, the better you can become at anything you do, okay, including beamforming. Okay, so this is kind of what is going on in 5G about this MIMO. Let's say distributed MIMO or network MIMO is essentially something like I said before. So you basically have a coordination between different base stations. Each of them might be having only one antenna actually, and you form, in this case, for example, you would form a virtual array of three antennas. Okay. You need a good backhaul connection for this, okay? Because you have to operate this as if it were a real collocated array. So you can't have problems in sharing information, and the connection has to be better and better if you want to achieve better and better things with coordinated MIMO. So what I mean is, like, there are different versions of coordinated MIMO, cooperative MIMO, as you want to call it, that actually are increasingly more complicated. Okay, so for example, one way could simply be, we don't even do MIMO really, we just coordinate. So when I schedule my users and you schedule your users, we talk to each other and we avoid clashes. So if we have users, for example, at the edge of the respective cells that are close by, it's a good idea we are careful, right, about using resources that do not overlap, for example. Then you have the situation, for example, what is called coordinated beamforming. So where you start also to play, you could actually have not only one antenna, but you could have multiple antennas at each of these masts. Each of them could form a beam. So it's like the coordinated scheduling, but also using now the multi-antenna degree that gives you beamforming. I mean the collocated multi-antenna. So it's kind of a hybrid between collocated and distributed MIMO. Okay, and then again, I could use beams to avoid clashes, right? So I can actually, if I am pointing toward the user with my beam, I have to coordinate with the other adjacent cells so that we don't point in the same direction, essentially. If not, it would create a lot of interference. Yeah. Now the third, there is another one, but I'm going back to that. So the third version of coordinated MIMO is called joint transmission, and that's the most ambitious one. So that operates as a real MIMO array. Okay. So what do I mean? So basically, whenever you have to share, for example, you're pre-coding with a data stream, okay, and you're pre-coding it by using for a channel state information matrix. Okay, for example, in zero forcing, you have to pre-multiply what you transmit with the inverse, essentially, of the channel matrix. Now, this is okay. I mean, you can achieve that if you have one array. But what if the array is distributed? Then you see you have basically to share the channel matrix and the data vector between all of these masts, right? It's like what you normally don't care about because you're actually on the same panel is now complicated because you have to share a lot of information actually across fiber possibly between things that are actually possibly kilometers far away. So you start to have problems of synchronization that are not trivial to solve, okay? And these are new problems because in the ordinary MIMO you don't have this, okay? Again, the story is always about increasing area spectral efficiency and capacity. Actually, the area spectral efficiency is something that kind of came up with, say, the 4G story. Before, spectral efficiency was the key metric. So the amount of throughput you can deliver over the bandwidth, bits per second per hertz. They add the square meter at the denominator, because it's also important now the spatial dimension. So you actually have a lot of, for example, small cells now, and so you want to make sure that also the area is accounted for. Okay, so you have basically to add that to the metric, and it's actually increasingly complex. Increasingly more complex this metric. It's not just about spectral efficiency anymore. You also have energy now. So you have bits per second per square meter, bits per second per hertz, per square meter per joule, right? And you could actually go beyond that because you could start to add cost, maybe. Okay, you could have what? You could have things like possibly you might want to add something to do with outage. So you might multiply by some stochastic thing. So you see the original idea of spectral efficiency was very simple, but even this metric has become more and more complex to reflect the kind of system we are designing. Okay, and actually MIMO traditionally is good for many different reasons. So it's good for spectral efficiency. You can push more bits in the same hertz of spectrum. It's actually good because you can actually provide good coverage with some of its techniques. It's normally more energy efficient, okay, than size of systems. Now you might ask, okay, wait a minute, why do you say it's energy efficient? Don't you have more antennas, so you should use more power? Actually, that's also the beauty of MIMO. You don't need to do that. So the power budget is set. So to be fair, the MIMO engineers, they do not use more power, okay, than the single antenna system. You use the same power and you split it, over the different antennas. So that is not changed. It could be that your signal processing is increased. The signal processing load is increased, so you do have power consumption in that sense. Another thing I found, the literature about energy efficient, we got a question about green networks yesterday. The literature about energy efficient networks is very much about the radiated power, which turns out to be a tiny fraction of the overall power the network consumes. It's probably 10%, something like that. So the other 90% has nothing to do with all the things we are discussing in this course. So it's about circuitry, it's about, you know, the power you consume just by powering up the base station. So, you know, to make more efficient, for example, the standby mode of a base station would be a big advantage in terms of the power consumption of the network, or to make, you know, more efficient circuitry, you know, more efficient signal processing, reducing the computational complexity. These are all good things. They are not reflected, though, in the power you transmit over the air. So you see, there is kind of a divide between the story of energy efficiency as we have been told and what is actually energy efficiency in the overall network. So you always have to keep in mind the system picture. Okay, it's not just about the wireless link, right? There is also the rest of the network. There is a nice paper from probably 2011. It's a magazine. They talk. So the author is called Auer, A-U-E-R, and they say some. Well, I can look it up probably. So we have it in our mind. I think I'll find it now. So it's basically, let's see, power consumption. It's a good paper actually. It's a magazine, so not so difficult to read, and it gives an idea of what. Yes, I think this is the archived version. No, this is the IIT Kharagpur. Okay, good. So that's the paper I'm talking about. So you might want to read it because I think it's actually a useful paper. Okay, so this tells you a bit what I'm saying now. Okay, that the story about the energy consumption is way more complicated. Okay, than what we normally assume. So now I'm not lying to say that it was an influential paper, because if you start to see citations and views, that tells it is actually a paper considered very useful by the community, right? I'm not an author, so I'm not doing any, you know, biased publicity here. Okay. So yeah, have a look because it's a good paper. Okay. What are the architectures? Actually, there is a point where you have to consider the backhaul, as we said. So network MIMO, it's not just about a single isolated array. You have actually a network of base stations that have to collaborate somehow, network of antennas. So you could do different things. So for example, you could coordinate over the backhaul. So you use fiber essentially for that normally. There are some techniques that have been there actually for a while, especially for indoor applications. They're called distributed antenna systems, DAS. Okay, another thing that is coming up is the cloud the cloud story. So you basically try to push functionalities back to the cloud, so far from the endpoint, and literally the antenna is just an RF dump element. So it basically collects the like receives the signal and then send the samples up to the central unit doing the real baseband processing. Okay, so there are different, we are going back to discuss this in the afternoon, sorry, in the next session, but essentially there are different ways you can actually split the functionalities between the, let's say, the antenna endpoint and the central unit. So it's not just one choice, you can do actually different things. A company that did very good work in this domain is Alcatel-Lucent. I think they're called Nokia Bell Labs now, yeah, in Germany. They're really doing good work on this. I think the lab is in Stuttgart, if I'm not wrong. Okay. Now there is a system level view now, right? So you do have to take into account coordination between antennas and possibly coordination between clusters. Okay, so what I mean is, like, you see, you always again have to keep in mind the system view. So you don't have just one array now, you have a distribution, right, of antennas or arrays, but that's not it, right? So you have other such collection right? So other such clusters of antennas in the system. So there is a multi-level now scheduling problem, right? So you have to decide what you do locally to coordinate, but you also have to coordinate with the others that are coordinating themselves, right? So you see, it starts to be actually a complicated thing. Now, what has happened is many of the problems we are facing in 5G are of a very high dimension nature. There are many things you have to optimize, possibly real time. So there is, I had a discussion actually with Professor Das yesterday, and you know, these discussions have been going on for a while in our community, is what is the right approach to actually optimize your network. It's more and more apparent that you can't use classical optimization all the time. Okay, so I think you have to rethink the optimization sometimes. You might have to go to more distributed techniques, okay, where you actually can only take some decisions that are informed by a local environment, okay, and then you basically coordinate with other clusters of entities. I think it's more and more unlikely that you will have a central genie coordinating everything. That was to some extent possible up to probably 3G. I think already 4G started, you know, with the HetNet story and so on to change the picture. Definitely 5G with machines and small cells. I don't see it feasible. I mean, you would need to collect so much information and to wait so much time to get the optimal decision that is useless. Okay, so you probably have to compromise the optimality with actually speed, okay, of decision. That's why, for example, AI is also a good thing because it's kind of a black box tool, so it can tell you actually genetic algorithms are good for that. They converge quite fast to some solutions that are not too bad. They're not the optimal, but you know, they're not that far off normally. So these kind of solutions are more and more you know, useful. Okay, so we are targeting to get rid of interference with network MIMO. Basically, yet you might have some problems in achieving such coordination. Okay, so the thing is, ideally, we would like to coordinate so that we, you know, limit interference. But in practice, we are not too sure, you know, that's always possible. And there is, for example, a limit given by the distance, the speed of light, essentially. So how far you can go with your size of the cluster, you know, depends on coordination aspects, right? So because you have to actually remember that any decision we are taking on the wireless side in the standards that are, you know, regulated by, that are like supervised by LTE, any of the standards have this unit of time, which is the time transmission interval, which is 1 millisecond. So the decisions we are taking should actually be within that time span, possibly shorter, right? So you can't go that far anyway. So, you know, that is one thing. Another thing is how many such antennas that are distributed you can put in the same cluster, because they all have to talk to each other and coordinate. So again, the numbers I came across, 3, 2, 7, 8. So we're not talking hundreds of such antennas. We are going back to that. There is a big divide between academia and industry here. It's probably one of the topics where the divide is bigger. Academia was very excited about it, and it's been there for a while. Honestly, even the first papers I remember on virtual MIMO, they go way back. Okay, we are talking more than 10 years ago. Not much after the original papers on co-located MIMO appeared, there were papers on this network MIMO. But the truth is, the adoption has not been so dramatic. Okay, I don't see such a big excitement from industry. It's also because I think they are okay to push up the cell edge throughput probably a bit. Not an awful lot though. But then you sacrifice a bit average throughput. So, I mean, it doesn't look probably worth the hassle, okay, from what I hear. Massive MIMO is another story. I think you know, the industry is much more reactive. Coordinated multi-point, that's my impression, not really. Okay, so something has gone wrong there. Okay, but it is still, you know, on the map. It just doesn't look to me that it's utmost priority, honestly, because probably there are complications and the gain is doesn't justify those at the moment. Okay. Any question? Comment? Yes.
Can we go back to the previous slide where the picture is there?
Yeah.
Now here when we talk about this coordinated MIMO in the first picture itself.
Yes.
Now the user equipment has to be talking to both the antennas.
Correct. Yes.
Because in all the pictures the arrows are shown to the respective
well, in this case, you see that's what I think we try to represent with this color. You're right. So, for example, in downlink, you see that both the base stations are talking to one phone, right?
The user equipment, if you are talking about figure like 4 to 7, it used to be in the coverage area of all those 7 base stations.
Yes, which is doesn't make. That's why probably the only gain you really see is at the edge, right? So when you start to have, that's probably 3 is not a bad number to start with, because you have kind of this overlap, right, between adjacent cells and cellular networks, and that's probably these are the users that benefit. Now, is that worth the hassle? That's exactly why industry is not so. You know, of course, on papers you can always come up with very nice models and show all sorts of gains, but in practice, you know, the companies are more pragmatic, right? So they really want to see what gives a bigger benefit before changing the system, because it's not a small actually ask, right? So you have to change quite a bit to do coordinated MIMO actually. So it's I don't see it as a very big success story. Definitely, massive MIMO is another story. Is another you know kind of story. So it's been much more influential already, though it's been around for less time. Waveforms, again, you see, so I'm being honest here. So even though I did work on a few of these techniques, I'm trying just to put forth what are my impressions and what I hear in the community. I don't think comp is, for example, if you have to pick the topic to work on, I would not do this at the moment, because I don't see it just becoming successful, you know, to a large extent. Now, maybe, you know, things will change in a few years. It's there. I think it's there in the agenda of 3GPP. I just don't see it as a big thing. I mean, at the moment, yes, that's my honest impression. I think I'm correct in saying that. Yeah.
And there was a talk around a few years back that the peers would act like a MIMO. I mean, the other user equipment in the neighborhood may contribute towards as a MIMO transceiver.
Yes.
For a user which is being served.
Right.
What I'm trying to say, does neighborhood user equipment become a peer for the?
No. I think yes. I think device to device is a better story. I mean, that's already more useful, and you can picture things where, for example, you need a fast communication, and maybe where it's difficult to provide access to infrastructure. It could just be an industrial environment where maybe you are shielded because of some reasons. And there, I totally see the point of having, you know, device to device, or for sharing of content, you know. And I think that's a better story, in my opinion. The only, I mean, the question you normally get is, why should people help each other? No, okay, it must be nice, yes, but
battery drain and all.
Exactly. So that's normally the critique, but I think technically you're right. I think that's definitely a better case, and you know, this is. To some extent, it's happening actually. Okay. So, any more comment, question? Yes.
Slide.
Sure. Yeah.
With the third case, millimeter wave MIMO.
Yes.
User equipment also will have multiple antennas there because it is beamforming.
Not necessarily. I mean, you to do beamforming, you need to have multiple antennas at either side. So it could be not needed actually. So you might actually do it, because if you are using millimeter wave, again, you could squeeze more antennas also on the user side. But to do beamforming, you don't need. Now, if you do beamforming at both sides, you get a better signal to noise ratio gain. Yeah, in this case they do. Yeah, but in general, you don't need that. It's just that if you want to get a bigger SNR boost, then it's better. Now, I did a bit of work on beamforming on the mobile side. It's normally kind of a nightmare, because you have very complicated trigonometry involved, right? Because I mean, when you have like a fixed access point, you can do all of your design, and you know, at least the guy doesn't move. But the mobile phone, literally, you know, it's really complicated. So I think it's probably it's kind of challenging still to think of a actual beamforming at the user side. I'm not aware really of much.
Here the CSA includes angle of arrival also.
Yes, exactly. Yeah, so I think you definitely at the access point it helps. I'm not too sure on the mobile side at the moment. Yeah.
Mentioning that the processing will be done on the cloud.
Yes.
What will happen to the latency?
To what? Sorry.
Latency.
Yeah. Yes, that's a good point. I think yesterday I kind of mentioned quickly that there is this tension nowadays in 5G between doing things more centralized or doing things more at the edge, right? And that's exactly because of what you're saying. So I think there are some good reasons to do cloud processing. One reason, for example, is sharing of resources. You don't need to buy things. You can pull things and just buy the service. That's cheap. You can, for example, shield your equipment in a convenient location instead of having them exposed and maybe and they could be vandalized, right? You could put the expensive baseband equipment in one shielded environment. So there are some good reasons to do it. I think one of the problems is latency. Okay, and in fact it's a bit against the philosophy of 4G already, because 4G was about pushing functionalities to the edge. Base stations are more capable than they used to be. Okay, they do more things. Cloud Run is against that because they assume kind of radio units that are very dumb. Okay, and again, my impression, the Cloud Run has been a big story in China. In other parts of the world, still, I think there is debate. Okay, so I think it's open for question what will really happen. But I think in the end you will not have, you will have probably to combine the two approaches depending on what you want. And it could be that things, for example, if you have a campus, so where maybe the distances are not so large, and that could probably make some sense. Okay, but again, yeah, it depends on probably the requirements. I think latency is a big factor. Totally, yes, absolutely. Okay.
So here the backhaul network, you mean optical fiber network?
I think it should be. Now the truth is, what we normally have nowadays, even in Europe, is copper. So they are slowly replacing. It's like copper, like yeah. So it's they are slowly replacing it. But for example, the rural part of the country in Ireland, I don't think they really have fiber everywhere, and that's true probably for many Western countries. I assume it's the same. If you make an exception probably for Japan and Korea, South Korea and Japan are normally much more advanced, right, than any other country in terms of technology adoption.
The MIMO architecture, it includes both wired as well as wireless.
Yes, definitely there is a part that has to do with the backhaul, and it depends on what you want to do. If you want to achieve pretty much, if you want to operate it as if it were one array, you have to provide very fast connections, and of course also distance plays a role. Even if you're very fast, still speed of light is the bound, right? So you cannot be too far. I think they normally assume optical fiber for this kind of things. Okay, and again, that might slow down the adoption of the thing, right? Because you would have to put in place infrastructure. So there are many things to consider if you really want to go down the route of network MIMO thing. Yep. Okay. Any other question, comment?
Here in cooperative MIMO, does it mean about the sharing of resources or sharing of information of relay?
You can have actually, there are several versions, okay? So there is basically the coordinated scheduling. It's pretty much sharing some information on the scheduling metric. So I'm telling you where I'm scheduling my users. Okay, so I give you, for example, a matrix, okay, with time and frequencies, for example, dimensions, and I put ones where I'm putting my users, and you tell me the same, and we try not to clash. That's not so much information, okay? I think if you go into things like joint transmission, where you are really operating as one array, then it's different, because then you have to have all the things we do normally, like data, and for example the processing, the coding, the pre-coding. Okay, so like for example the 0-4 symmetrics, that has to be shared. Okay, because you have to have your piece, I have to have my piece, so there has to be a tighter sharing of information, and the numbers are not that promising in that sense. It's really requiring a lot of bandwidth. I'm going back to this in the next lecture, but again, that's a big limitation, okay, of these techniques. Okay, I'll move on a bit. You can always, come back with other questions later. Okay, so just quickly, okay, I'm going to recall the flavors. So this is coordinated scheduling, the one I just talked about. So it doesn't have to be just time and frequency, it can also be power. So for example, let's say you have this situation where essentially the cell C is kind of disturbing cell A and cell B because the users of A and B, they are interfered by cell C. Let's say this is downlink, for example. Okay, so what they could do if they talk to each other somehow, it could be that cell C zooms in, right? It reduces the power, and that's a very simple example where the coordination of to have this kind of network approach to multi-antenna is a good thing. Okay, not that complicated, but it can actually benefit. And again, you start to see what I meant about cell edge. It's normally about the users that are in the overlap region, right, that benefit, of course. That's kind of the point, right? The users at the cell center, which are the ones that contribute the most to the total throughput, those suffer, because you are doing things to help the users in trouble. So it's a trade-off, right? It's like a government policy. If you want to help, the lower layer of the population, of course, you might have to tax more rich people, right? And that's there is no magic wand. You have to compromise something. Yes.
There is also a lot of time going on in this coordination between the different.
Sorry.
There is a lot of time also getting spent, right? Coordinating between different.
Yes, but again, it depends on. You could have like simple things, like for example, you can play with the granularity of the action. So you could say, for example, it could be as simple as you stay on, you switch off, right? So then, of course, the more complicated your strategy you want to become, the more time is involved. Yeah, because you have to share more information. But there could be things like for small cells, for example, this switching off is something that people are considering. Now, for a macro. Not. Yeah, that's a different story, right? You can't really switch off macro too much.
One more question on the previous slide, sir.
Yeah.
Suppose if we have a D2D communication inside a particular cell in
Yeah.
this figure.
Yeah.
Suppose one device want to communicate with the other device, the resource should be allocated by the cell base station. You can renode it, or the device can able to.
I think. It depends on the level of power. So if you are, there are two flavors, I think. If you are using a high power in the D2D link, then you should be told, or you should coordinate with the base station. But another approach is to use underlay communication, right, or something like ultra wideband. So where you have a very thin power, then probably not, because you are not going to disturb the base stations, okay, but the base station should be controlling what happens, right, because if it disturbs the service of the other users, then it would take action. But I think people are considering also underlay, which is normally easier in terms of coordination. Yeah. Okay. Coordinated beamforming is pretty much the same thing as we just saw, but you actually exploit the capabilities of MIMO at each point. So this is a multi antenna, right? So you have actually the network MIMO aspect, because you have two masts that do coordinate, but each mast will have a MIMO capability, so you can form beams, and of course you get the benefits of beamforming translated at a system level now, right? So if I'm serving my user, I can also put a null toward another user that I'm not serving, and that's good, right? I'm boosting in terms of the system SINR, if you want, I'm boosting the S part, but I'm also reducing the I part. So both of the numerator and the denominator of the fraction benefit, right? Yeah. So again, you do have to share things like I'm transmitting in this information. So again, yeah, going back to the question about coordination and time needed, it depends on how granular you want to be. If you want to, have like inform about your precision degree by degree, that's a lot. But maybe it's enough to have it, I don't know, 30 degrees by 30 degrees, right? But these things are what you have to share. So you would have to imagine something like a vector or a matrix where you have ones when you are using, right, that portion of space, and 0 in other situations. Or maybe in LTE probably what you could do is like you have a set of pre-coding matrices, and you inform the others which one you use, which is not much in terms of information, because maybe you have 4 matrices, you just have to share 2 bits, right? And the other guy will know what you're doing. Positions are very much known. They are known to you already. If you Google up the base station positions in Kharagpur, you'll find them, right? Most likely. So these are not big things to ask in terms of information anyway. This is a different story. So the coherent joint transmission, that is ambitious, and it requires a lot of information sharing, because you are literally coordinating at the signal level here. Okay, so you have to exchange the sound state information, the data, and you are essentially, creating the signal distributedly, right? So I didn't do really work at physical layer in this sense, but it's it sounds easy, but it's not, okay, because you have actually issues to do with coordination, synchronization. Also like definitely that's where the backhaul will be the most, playing a very big role. In the other cases I mentioned so far, not really. I think here you definitely need fiber or something like that, because you are sharing a lot of information. Okay, so if you don't have a good backhaul, you cannot do this kind of techniques. Again, if you just gain a bit in cell outage, is it worth the hassle? Possibly not. Okay, I'm being honest here. I think academically, yes, there's been a good amount of work.
In this case, the same information is being transmitted via 2 cells to the.
You can actually, my understanding is that you can do pretty much what you want. So the same things you do with MIMO, you can do here. So it could be the same information if you are doing diversity, but it doesn't have to be. Okay, it could be multiplexing where you say, I transmit this part of the data stream, you transmit that part. We are really playing with the advantage given by macro diversity here, right? So you are seeing a different channel for sure here. So, and then of course there are the system advantages, controlling interference, sharing the load maybe, but ideally, hypothetically, you should be able to do what you do normally. Okay, so you can do whatever you want actually. Yeah.
Where does all this coordination take place? This intelligence, everything will be taking place at the central place, or it's being pushed to the edge? Everybody is equally intelligent?
Yeah, good question, because somebody has to coordinate, right? I think what they normally assume is like it's kind of a peer structure. So the base stations in the cluster would have to basically arrange that, okay, and they would be equally intelligent. Now the question is, if you move up one level, who does the coordination though, right? And again, you could have more distributed approaches, like the cluster somehow sees what the other clusters are doing and react. Okay, that might be suboptimal, or you might have another entity. I think architecture aspects are important. Yeah, I don't know if they were really discussed too much though, but I think it's a valid point. What I think they are assuming now is that somehow there is an equality of capabilities. Okay, and it's like there is no special antenna in a collocated MIMO array, right? They are all kind of doing their job, and it's the same here, with the addition that they are not in the same place. Okay, so this is again sort of more to do with mobility. So you actually can also coordinate the serving antenna, okay, by using similar techniques. And This has happened for a while now with handover, right? We all know that, but I think here the idea is that you push it to for example, to combine possibly with Cloud Run, stuff like that. So where you have, you can control a certain area, okay, and then you have the remote radio heads that are the serving points, and then you just check who is serving the user at any time by exploiting the cloud capability. That's my understanding. To be fair, that's probably the least advanced. I didn't see an awful lot of work in this. Again, you see, you have to consider that in our field it's so broad that you can't have the ambition to know everything. So I do not work so much on comp. Okay, I did a bit of work. So, but still, you get an idea what is going on. You know, I think this technique is probably less developed than others. Okay, and it could be to do with the fact that the Cloud Run story is still not settled. Okay, maybe that's the reason. But it is one version of coordinated multipoint. Yes.
From the EMP to the remote radio, there is a backhaul.
I think normally they are assuming that. It depends again on the. I'm not sure you would need that though, because I mean in this case probably you just have to. It's more like handing over, right, to the next remote radio head. So you might not need backhaul. It depends on how fast you want to do things. I think in terms of information exchange, might not be too much here, but you have to cope with mobility, so you have to be fast. So maybe.
Then I
Yeah.
don't find any difference between the coherent joint transmission and the dynamic configuration.
These guys do not necessarily transmit at the same time as one thing. It doesn't have to be. I think it could be, but essentially here they add mobility to the picture. So they are changing the point of service. Okay, but it doesn't have even to be joint. Okay, it could be just that you are handing over, right, and it's just exploiting the remote radio head and cloud story, I think. Okay, but I don't think this made such a long way compared to other techniques. I think probably the most immediate and useful ones are the simpler ones. You see, the gains do not justify too much work. That's the problem. Okay, so I think what I think could happen is that they implement the simpler ones in cases where the outage is really important. Okay, where they really have they would have a big problem if some users are in outage. Then it would justify maybe sacrificing a bit the average throughput. So I'm thinking maybe techniques like the services like the ultra reliable low latency could benefit by these things. I don't think this is a technique for mobile broadband. I don't think it goes well with that. Yeah. I mean all of these coordinated multipoint. I'll just maybe do no. This is a new thing, so I'll stop here. Any last question? Then we take a break. We do have the Q&A session starting at 10:30, right? So you can just come in and we can continue to discuss if you want. Okay, thanks. Okay, so welcome back to the second session of the day. So I was told I have to finish 10 minutes to 1 because you have to catch the bus. So we'll finish, 12:50 more or less. Okay, so let's go on with the distributed MIMO story. So now, as I mentioned a few times, implicitly when you talk about coordinated MIMO, you are talking about interaction between wireless and the fixed side of the network, right? So there is this problem of fixed and mobile convergence, which cannot be neglected. Essentially, this has become something very important to consider, not just in the context of coordinated MIMO, but also because you have more and more things that have to be connected to the backhaul. Okay, so the same thing happened with let's say heterogeneous networks. Okay, flexible like small cells. So these things actually have introduced the issue whether it's economic and even feasible to have all of these, you know, points of access connected to the backbone. Now this picture I'm showing here is actually interesting because it tells, you probably saw this before, it tells how the wireless data rate has increased over the past 50 plus years, and it has increased by 1,000,000-fold, but only 25 times due to spectrum and efficiency, which is essentially what you do with physical layer, okay, MIMO and stuff like that. So the overwhelming majority of such an increased factor is due to cell densification. Now, no matter how smart is the engineering you are about, the easiest thing is always to get transmitter and receiver closer to each other. You can't beat that, that's physics, right? So if you can bring the transmitter closer to the receiver or the other way around, it's always the best thing to do, and this is testified by this figure. Of course, they all multiply, so if you multiply 25 times 1600, you get 1,000,000. So they're all important. Of course, if you get rid of efficiency, you would decrease the data rate by 25 times, which is very bad. But what I'm just saying, you have to keep in mind the context always, okay? And it's actually kind of myopic to struggle so much to increase the efficiency or to increase the spectrum you can use, and forgetting that the giant leap toward higher data rates is given by actually shortening the path lengths between base station or point of access and mobile phone. It's always like that. That's why you have Wi-Fi, that's why you have millimeter wave, that's why you have small cells. They are all, you know, beating you know, the same bush, so to speak. So you have to consider this when you do your design. So this fixed mobile convergence is way broader than this coordinated MIMO story. It's also, okay, you talk about densifying the network. Can you even do that? Can you have really fiber going everywhere? Okay, that's where, for example, they are considering something called self-backhauling. Self-backhauling means you are using the radio spectrum to do both access and relaying possibly information to the core network. Okay, they are considering that. Millimeter wave is a way to go about that. Okay, so you might not have the possibility to have backhaul all everywhere, right? You see, there is also a revenue problem. Okay, it's not just technical. So when you deploy a fiber, it's expensive, okay, and you really want to get the best out of it in terms of profit. So for the larger cells, as it used to be the case till now, that's okay because you are serving quite a few users, okay. If it's let's say home broadband case, you are serving maybe in a building, few apartments, maybe hundreds of people, right, in some buildings. Think about a guest house here, right? Makes sense, right, for them to deploy a fiber because they know that they are going to get, you know, quite a few customers. Or a macro cell, you have definitely possibly 1,000 of users, few hundreds at least, right, that are being served. But what about if you start to have a small cell that serves 2 or 3, right? So you see, the catch is that you have to be careful doing the business analysis. And as I said before, I think it's very rudimentary, the work that has been done so far, if existent at all. So in my opinion, a good topic for a research project or a PhD would be finally filling this gap, doing a serious cost analysis, of course associated with technological analysis because we are engineers, but maybe having a supervisor from business and a supervisor from engineering, something like that. I see very little of that, and surprisingly so, because it's a very big deal. You know, we have all of the metrics in the world and all of the studies in the world about technical aspects. I didn't see a single good paper about these things. Okay, again, open your mind. Okay, there is probably a world of opportunities if you just do that. So I think to have a cost analysis embedded into the technical one is very much needed, and it might actually tell you how much you can densify the network, how much you can do coordinated MIMO. We know kind of technically what is the limit, but we don't know whether that limit is sustainable. Okay, we know, for example, that you could deploy, say, possibly a base station every few square meters. We know that. Okay, you know, you might have to cope with interference, but we also know how to do that. But now the question is, how do you connect this small cell? How do you connect this antenna in a virtual MIMO to the rest of the network? That's something you cannot neglect. A lot of the wireless papers, they are just saying magically backhaul will take care of it, which was to a large extent true so far, but may not be true in the future. So these are things to be definitely considered in 5G and beyond. So what they do to deliver actually the information, the data to the edge of the network. The edge of the network, I mean the wireless part, right, the radio part. They have actually what they call, I mean, one possibility is to have these passive optical networks, which imply limited use of electronics. Okay, so I'm not, again, we have a very good team in this area, so if you're interested in this domain, you can ask me and I'll get you in touch with those guys. But they are trying to share, okay, the fiber because it's expensive, so they are basically bundling. Right, they have these splitters where they basically, it's like a multiplexing, physical multiplexing, and they serve different points of access. So they bring the data to some point, and then they split out the fibers to serve different dwellings and stuff like that. Okay. One thing actually that is very interesting about the optical side of the network is that they are kind of playing with capacities we can't even dream about in wireless. Okay, so they do have their own modulation, MIMO techniques and everything, but they are basically playing with physics again. They are using a guide, so the dispersion and the multipass and all of these nasty things we see in wireless are not there, so they can really focus, right, and they use the proper frequencies, and so they can really, boost capacities. They've been talking about terabit per second for a while, okay, while we are still struggling with few gigabit, right, per second, and no way, for them it's peanuts. Okay, the problem though with this story, infrastructure is very heavy. You have to deploy the thing, right, you have to dig, you have to get permission, it takes time, money, and flexibility is not there. Okay, but the very fact that you use a guide, you are constrained. Wireless is a world of freedom and opportunity. So the two things go kind of complement each other. When you have capacity, you don't have freedom. When you have freedom, you don't have capacity. So, even philosophically, the two things have to be co-designed. Again, not so much work. Okay, you do have lots of conferences, papers, communities in optical and fixed network. Same with wireless. This course is a good example of what I'm saying. You don't really have the optical counterpart, right? And I think it's time to change this mentality, and it's not such a big divide. In fact, it's all about communication engineering. So we are very good at creating boundaries artificially, apparently, but we shouldn't do that to evolve, right, the technology and science. So I think if you have, again, a project where you have a supervisor from optical or a PI from optical side, and a PI or supervisor from wireless side, is a very good idea. You can come up, with new problems and good a new space of work, and you can make a real impact, because this is, again, very relevant nowadays. Okay. So they have their own standards. So for example, a common one they use for this Cloud Run, and coordinated MIMO story is called CPRI, Common Public Radio Interface. Basically, the digital processing is done in some unit called baseband unit, which doesn't have to be co-located with the RF front end. Doesn't have to, actually. Normally it's not. And you can literally bring it anywhere you want, okay, provided that, of course, you take into account delay and you have the fiber to do that. But essentially, they decouple the RF part, so the antenna, say, part, to the from the baseband part. So the intelligent processing is not done where the antenna resides anymore. Yeah, that's the idea. So where do you put this baseband unit? Well, fiber can easily cover distances of few kilometers, of course, taking into account delay and so on. But you know, you can have like very long fibers, right? You can have fiber without actually significant problems that are up to hundreds of kilometers. Okay, they do that. So you could, for example, put the baseband unit inside the building where you have security in the sense nobody goes there to tamper, vandalize, attack the thing, right? You also have kids doing stupid things sometimes, right? Or some people. You can't have that if you are securing your equipment. You don't have weather impact, right? It cannot be struck by a lightning or stuff like that. It's kind of, again, in a shielded environment. So you don't have to be constrained anymore by where the mast is. The mast, of course, has to be close to the user, but the processing, once you decouple it in this way, doesn't have to be. Yeah, so that's the idea. You can put more than one baseband unit, so you don't have to do this one-to-one mapping anymore. So in the past, you were constrained to put one kind of baseband unit where the mast was. Now you can pack all of them in a secure place, and that's good. I'm thinking for people that really care about their equipment, and that's a good thing, actually. So right, and you can start to do also more complicated things. Now you see this again is similar to what I said with small cells, where you bring the resource allocation to another level, another dimension. This is also kind of a resource allocation problem now. Which baseband unit located where should serve which mast located where? So this is a new scheduling problem altogether, right? Scheduling problem, and we didn't have this before. So you see, you can start to play with network function virtualization. You don't have to have a physical association between a function and the resource. You can start to do pooling, statistical multiplexing, right? Not all the masts and all the baseband units will be used all the time. You don't need to have such a tight, fixed, rigid association. You might have a pool of baseband units, and you know, for example, that at any time, let's say you're serving 5 masts, but at any time, you know, statistically, only 2 will be active, right? So why would you have to have 5 baseband units? Maybe you just need 2. And you start to, it's like resource sharing, really, all over again, right? So you see, there are actually interesting concepts in this space that are coming up. Okay, any comment, question? Okay. Yeah, Cloud Run is one example. It is not the only thing you can do, but it's probably the most famous one in this space. And you really push, let's say, this concept of decoupling baseband and RF to the extreme. So you basically use things like the IBM cloud, stuff like that, right? So you have all of these computing capabilities that are, you know, online and shared. And you could think of signal processing as just another thing the cloud can do, right? That's the idea. And it doesn't have even to be anywhere close to where you are actually using it, keeping in mind that you have delay issues and so on, right? Or you can even think about giving it up altogether. If there are people doing cloud services and they're good at that, buy them, right? That's a big saving in the cost, right? Actually, there is this concept of virtual network, right? Virtual operator, that means to the extreme, you might be able to operate a network and sell the service without owning anything, right? You might rent anything. There are actually operators like that. You might just have the brand. I am operator A, and I give you this service, period. The people don't care, but you are literally not owning anything. You rent the spectrum, you rent the antennas, you rent the baseband, you rent the cloud, right? So you own nothing. I mean, so these things are actually coming up, okay? And it could be a way to reduce the barriers of entry to the market. Now, one thing that has been invariant to any country and any time of the cellular communication story, it has always been that there are 3, 4, 5 operators per country. No matter the size of the country, no matter the development of the country, it's always like that. I think in India, how many do you have? Do you know? Airtel, the one I know. Any what other operators do you have?
BSS. Vodafone.
Many more?
Reliance. Geo.
Okay, India is a huge country, so I give you the benefit of. But you see, I mean, it's like we are not talking hundreds, right? So I think in Ireland we have 3 smaller countries, so it makes sense. But you know, of course they might actually target a segment of market. Maybe some operators are more about young people, some others are more about business people. I don't know, but you are not going to have too many, and there is a reason for that. It's not that this is a magic number. It's just that the costs involved are so big that you can't simply afford it. So now, what people are saying, again, it's a bit visionary. I'm not sure if that really will happen soon, but they're saying it doesn't have to be like that forever. If you start to decrease the costs, you know, to buy a spectrum license, to buy masts, right, to have this, the need to have these baseband units operated by you, the cost could be sensibly less, right? You might not have to spend so much money, so you might start to see a proliferation of operators. And I don't know how you feel about competition, but it's probably not bad, right? You might actually bring better things at a cheaper cost. So maybe it's not so bad in the end. But you know, still this is more futuristic. So an important thing is to decide who does what, right? Okay, we share, but exactly what do we mean? Essentially, you have MAC and physical layer functionalities, and you have to decide what is done by the radio resource unit, so let's say the RF front end, and what is done by the baseband unit. And this baseband unit could be, you know, anywhere in the cloud and so on. So you have these vertical lines here. You see phi 1, phi 2, blah blah blah. They're basically corresponding to different proposals. Of course, the functionalities you have to do are always the same. It's a communication system, so you have to do MAC, you have to do modulation, you have to do basically error correction, right? You have to do these things anyway. Now the only question is, where do you put the blocks? Okay, and depending on your requirements, about probably I would say about performance versus delay, I guess that's what probably is the trade-off here. You might decide to put one thing on the one side of the fence or the other side of the fence. For example, what 4G did was to push as much as possible to the base station. It's because I think they also focus a lot on being fast and responsive. But there are advantages also in not doing too much there and to push things maybe more to the cloud, to the center, or to the fixed part of the network. In that case, if you relax a bit the delay constraints, you might actually have a better deal in terms of efficiency, for example. Okay, or you could, for example, have a better deal in the sense you don't have to have a one-to-one mapping of your phi and MAC blocks to the mast, right? What I was saying before, you could start to pull things, have less of them, playing with statistical multiplexing, and you spend less money essentially. But of course, you are pushing things more far away, so it takes more time to respond to a request of service. Yes? Make sense? Yeah. Okay. So yeah, I actually mentioned here the person in my university that is expert in this field, so you know you can check his works if you want. Okay, I got a question already about these numbers. Now I'm not to be held accountable for these numbers because I got them from this guy. So I think they kind of make sense. Okay. But they you know, he's the expert, so he would probably tell you exactly where these numbers came from. But the important thing here is like they made some calculation, sort of back of the envelope, but you know, with some realism about the data rate it would require to do these kind of transmission schemes. They are calling them front haul to distinguish them from backhaul. So traditionally you have the access point, the base station, and then you have immediately kind of the backhaul, right? That's what we have. Here, since you are kind of stretching the radio element from the baseband, you have this kind of in-between link now, physical link, which is what they call frontal. So you have the access, radio access, frontal, which brings the radio unit to the baseband unit, and then you have the backhaul, okay? So the whole part stretches now. You have also the front hole. So they made some calculations to see how much data rate you would require to do this kind of techniques. And okay, it seems to me like the Drake equation for yes, nothing to do with that, but it kind of struck me. Okay, this probably. I hope it's a bit less speculative than that, but yeah. So I think we had the same feeling then. So anyway, they have basically, they tell you something to do with sampling rate, number of antennas you use, the overhead, okay, due to line coding. What else? The digitization, like the quantization, right?
Samples in terms of optical signal.
Yes. Well, yes and no. So basically, what they do here, they convey the radio signal to the.
There must be some conversion.
There is a conversion. Yes, they do some conversion. I think they do radio to electrical, right? And then they bring it actually to the. Yes, I think you're right. So anyway, these numbers wouldn't tell so much. Okay, they are what they are. We might agree or not, but the interesting message is like, if you actually compare the actual rate you deliver, yes. Yeah.
It should be 2 NQ because it should be 2 NQ. In the formula, it should be 2 NQ because we are sending I2 samples. And
could be, yeah, could be. Could be, but the important thing here is like again, there might be some time variations, but the order of magnitude of the thing is correct. Okay, so what I want to stress here is like if you compute the rate you are delivering over the radio link, it's immensely, well, not immensely, but much smaller than the rate you require to operate the frontal itself, much smaller. So you are basically not having a good deal in terms of efficiency, because if you take the ratio between the frontal rate with the formula we just saw, okay, with some tiny adjustments, it's not going to change the picture anyway. And then the RAT, the radio access technology rate, for example, if you have 64 QAM, you have 6, right? A 6 factor, right, in the spectral efficiency. And then if you have 100 megahertz, again, that is multiplying, right, your rate. And then 8 antenna, 8 MIMO, 8 by 8 MIMO, multiplying by 8. So these are the things you can do to boost your radio access, right, throughput. If you compare this with the frontal, it doesn't make sense, because you are basically wasting an awful lot of bandwidth to do this. So you see, it's not the best way to use fiber, probably. Might be happy with that, but I'm just saying from an engineering viewpoint, this is a terrible system. Actually, I was talking with a very senior guy in British Telecom. He's probably the inventor, actually, of passive optical networks. He's very knowledgeable about all of this domain. He starts to itch when he hears these kind of things, because it's a total waste of the system. Okay, so he doesn't like it at all. And that's the guy as senior as you get in Europe in optical networks. Okay, so we would still have to convince those guys that this is a good deal. And this guy is an academic. Now he's been working with British Telecom, but now he's a research professor with us. So if you can't even convince an academic, I'm sorry, forget about convincing industry. Okay, so Alcatel-Lucent is very positive about this. Again, I'm not too sure, okay, where this is going, because there are contrasting feelings whether this is worth the effort. Okay, good. And then you have the latency issue, which we already touched upon a few times, right? So essentially, let's say you have a repeat request system, right? You have two retransmissions, okay, HARQ. You require that the messages between the user interface and the baseband unit are acknowledged within 3 milliseconds, okay? Now, there are also processing units, each of them taking some time, right? You are, for example, inserting a cyclic prefix, right? You are doing modulation, you are doing coding, all of these things, they are not instantaneous, right? So it eats up, again, the budget. So typically, what you should have to comply with this requirement is that you should not exceed, for the frontal transmission part, something like 200 to 400 microseconds. So we are talking something like 0.2 to 0.4 milliseconds. It's because you have this 1 millisecond thing also, right? So and then you have these 3 milliseconds. So you are talking milliseconds anyway. So you cannot take much more than that, which also bounds how far you can go with the fiber. It's not about attenuation. The optical guys are great at that. They can get you going, right? They have these transatlantic cables. So no worries about distance. The problem is delay. So that's already telling you hardbound about the area you can think of with to be covered with this CPRI, Cloud Run stuff. By the way, it's not too bad, right? 20 to 40 kilometers is pretty decent. So very popular ideas in China, by the way. They are really interested in these things. I suppose it has to do probably with the geography of the country. I suppose when you have a large area to be covered and you want to be efficient with resources, these things make kind of sense. Again, efficient economically. Efficient technically, that's not true because we just saw it's a very terrible efficiency. Okay, there are other ways though to do it. So they have like the digital radio over fiber and analog. I think the digital is a very bad deal. It has good point in terms of doing things digitally, but in terms of efficiency, it's really bad. So you might have a better deal if you do analog radio over fiber. So there are a few variants. Okay. Yeah.
It's a sort of a compression or a PDCP?
So this is packet. Is it data convergence protocol? I think. Yeah, I think so. Then you have radio link control, and then you have MAC, and yeah. But they are not considering to move that to apparently to the radio. That's already on the. You know, they are not going to move that to that end anyway. Apparently, some proposals they say we should do MAC in the baseband.
Some operations in physical layer and some operations in MAC layer.
Yes, yes. I mean, all of these lines are possibilities. Yes, and I suppose it has to do with probably economical considerations, you know, and there is always a trade-off between being efficient and how fast you are, right? So I think it depends also on the requirements. Yeah, there are actually good works from Alcatel Germany about this. They have been talking about things called light radio, light like light. So they did quite a bit of work on this in the past few years actually, and yeah, I can ask my friend if you want more information about this, but it is a very popular topic in China, to some extent in Europe. I'm not fully aware of US picture. Okay, that's all there is about distributed MIMO, and then we can move on. Any questions? No? Okay. So now we go to massive MIMO finally, okay, and then today we have the tutorial paper on this. I read the paper myself, okay, of course. I think some parts are not so easygoing, okay. Some parts are easier. I think the beginning of the paper is pretty much smooth sailing, then it starts to get a bit complicated. I wouldn't worry so much. I mean, I can tell you a bit about the numbers if you want, but I wouldn't say that's the main point of the paper, okay. They have some considerations about the coherence time, right, and for example mobility, so the pilot length. So there is a reason why they have the specific numbers, but the main idea was to go to the founder of the technology and hear his opinion, because Marchetti is actually the pioneer. Okay, so it's a good read anyway. So don't worry if you didn't get all the details, because that's not the point of the paper club. So the way I will organize that, up to you how you form the groups. I would suggest 4 or 5 people per group, not more than that. And I would give you kind of an half an hour to discuss among you what is your understanding of the paper, what are the points you want to put forth. One task I would give is to elect a chair, like a captain, if you want, of the group, a group leader, and then I would have a second half of the hour where I would discuss mostly with the relays, right, with the group leader, just to keep some control on the discussion because you're many, but the others can also interject, right, and talk if they want. And then I would suggest you to scramble groups next time and to change leaders. So I would like to be you know, as heterogeneous as possible, because one factor I always see myself when you go to conferences or this kind of events with colleagues, you tend to cluster with your colleagues, and there is a good reason for that, right? Because you're more familiar, you're more comfortable. But try also to mingle a bit, at least in this occasion, okay? Of the I will not ask you to scramble during dinners and so on, but at least during the paper club would probably be not a bad idea. Maybe next time, okay? So and try to get different people to stand up as team leaders. It's also a good exercise about interacting and proposing your ideas, right? And trying to summarize the team view. And hopefully we'll get some interesting discussion. Okay, that's the idea. But it's not like really, I'm going to interrogate anybody about the sampling rate. And if you want, I can tell you about that. It's a bit beside the point, okay? Good. So what is MIMO? We know, okay? One transmitter, one receiver, more antennas, more than one antenna at both sides. Yeah? So you get multiplexing gain because you parallelize data streams. Yes? That's also that's what they call point-to-point MIMO. Multi-user MIMO, you have one transmitter, multiple antennas again, multiple receivers. Each of these receivers might have multiple antenna or not. Okay. What they call multiplexing gain now is the sum of the parallel streams. So the parallel streams are now not bound to be transmitted to a single location. Of course, you transmit them to different locations, but by and large, similar story. Okay. Now, what is massive MIMO though? Now, a possible definition. Now, these guys are very much the world leaders in massive MIMO. Okay, it's among those. So there is Marchetti, and that Bell Labs guys, and then there is the Swedish guys. They are, I think, in Lund University. So Björnsson and Larsson, these guys are, definitely the leaders. Okay. So whatever they say. So there is a link here where they have, I think, more material. So this. ma-mimo dot blah 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 is the website where they collected pretty much all the material around in massive MIMO. There are also some of our papers, okay? So they kind of collect all the stuff, okay, that is relevant.
So that spatial multiplexing is same as that of the spatial division multiplexing, or both are one and the same or different?
The spatial
multiplexing and spatial division multiplexing.
I think normally when you mean spatial division multiplexing, I think they're probably the same. You could also think of access dimension. In that case, they are not. So you would have multiplexing of users rather than streams, okay, over the same point. But I think SM and SDM are probably same story. I think, yes, that's what I would say. If you have SDMA, then it's another story. Then you have the access bit, yeah? You agree? Disagree? Yeah? You fine with it? So the definition is actually like that. So you have, it's a multi-user system, first of all. So massive MIMO is still a multi-user system. You actually multiplex data streams over a channel with favorable propagation conditions. Now we are going back to what they mean by that. They use time division duplex. And again, we are going back to why that's an important assumption. You will need pilots in uplink to estimate the channel. Okay, so it's kind of packed as a definition, but I think it's very clean. Okay, it's neat. So it tells you all about massive MIMO definition as it stands. Okay, we are going to elaborate more on these aspects. Okay. So to be a bit more technical, okay, so a base station is equipped with many more than one antennas. You will not talk about massive MIMO if you have 4 antennas at the base station, okay? So you are talking possibly 50 or more, okay, at least. You would communicate with each of these base stations would communicate with K single antenna users. So single antenna is important. So they are not playing with the multi-antenna side, multi-antenna dimension at the user side. That's an important thing that led to the adoption of massive MIMO in the standard, because it doesn't mean that you have to change. The user does what it does normally. You don't have to change the user, okay? You need the number of antennas at the base station to be larger than the users, possibly much larger. What do we mean by much larger? Normally 10 times. Definitely more than 1 though, okay? Yeah. And then you have techniques that are very simple. So the fact that you have so many antennas kind of helps you to get rid of inter-user interference, of noise. It kind of makes the channel better. So you don't have to struggle to do very complicated things like dirty paper coding or non-linear transmission and reception. The idea behind massive MIMO is really to use very simple signal processing. Okay? So you actually get a long way by using linear techniques. It's different compared to the MIMO we are used to. Okay? There are reasons for this. Okay? Hopefully we will elaborate a bit more later. Okay, the shape makes a difference. Okay, now normally as I'm a DSP guy originally, we normally don't care about how the antennas are arranged. We say, okay, they are spaced. Maybe what we normally have in mind is a linear, like the first guy, A. But that's not the only thing you can do. If you need to pack antennas, why not to use the 2D plane, right? So you can start to have many more antennas. And depending on how directional you want to be, you might start to wrap up things. So for example, if you have a panel, what happens is that the beams are going to be more directional if you do beamforming. If you wrap it up, of course, you're kind of bending even the beam if you want, right? So depending on what is the scenario, if you have to be more directional, less directional, you can start to design different shapes, yeah? So you can have hundreds of radiating elements. The problem is you still are limited by how many RF chains you have. That's why they have this hybrid beamforming in millimeter wave, where you have a part of the processing is done in the digital domain, part in baseband, and part is done on the RF domain. That wasn't there before with MIMO. So you start to have to cope with the fact that, well, it's really a lot of RF chains, okay? So that's not completely resolved, this problem, okay? But let's say maybe millimeter wave is a bit more special. I think they are still probably hopeful to solve things digitally at lower frequencies. I think they are doing that. So for sub 6 gigahertz frequencies, you don't need these hybrid techniques. You can still handle the processing in the digital domain. That's what they say at least, okay? There are very nice test beds in Sweden, in US, in a few places actually. So they are actually testing the thing and it's there, okay? These different shapes, they help also to pack more antennas, right? If you need a lot of antennas, you can make sure that each of these radiating element is at least half the wavelength far apart, which is what you need to provide independence of the channels. But nobody told you have to stick on a line and then you run out of space in the mast, right? Who told you that? I mean, you can have a panel, you can have 3D things, you can have a sphere. You see, you can start to use geometry, right, to your advantage. Of course, it depends also on the pattern you want to create. It's pretty much, I know we have some 3G experts in the room, so what I discussed with the people working with me on Massive MIMO is pretty much like a CDMA system. So what they do, well, even if maybe it's not so intuitive in the first place, but what you do, you are kind of using, essentially it has to do with the vector channels. This is all you need to decouple the users, okay? And each of them will likely have something that doesn't look like the other. So each of them will have a vector channel which is like a code, which is sort of orthogonal to the other channel gains, provided there is spatial separation and provided you have enough antennas. By the, there is a theory, it's called random matrix theory. It tells you essentially the law of large number kicks in with matrix and vectors, and if you increase the dimension asymptotically, I say to infinity, literally there is no interference. But at reasonable numbers, like maybe 50, 100 antennas, you start to see very little correlation between these vectors. So effectively, they are behaving like codes, physical codes if you want, okay? So it's a way to see it, okay? So why do we need it? For example, you could think of concentrating your energy in a specific location. So if you have a lot of antennas, you can start to become really precise about the beam you create and where you direct it. So since we know, for example, that scattering is good, if you can collect all the energy associated to the copies of the signal, you could think of identifying the scatterers, transmitting toward them, and then playing with multipath this way. and you become very precise because of the degrees of freedom due to the number of antennas. Yes? I think I have a figure. Yeah, this shows what I'm saying. So if you have 10 antennas on the left side, okay, you see this power map, right? This basically it's the field strength, right? It's the power you receive. So it's kind of all over the place, right? You're not really directive on the left side. But what happens if you basically do some simple techniques, again linear processing, with 100 antennas? Well, if your target is at the center of the plane, you get there with a power that is definitely higher than the surrounding regions. So that's the visual representation. There is the paper where they talk about this, of the capability of massive MIMO to concentrate the power. That's what they mean by pencil beams. You get beamforming to the next level in a sense. Okay?
Even if it is a pencil beam, ultimately the beam, once it comes out, it will broaden.
It will. You're absolutely right. In fact, they talk about it in the paper, I think. There is something to do with the angular spread of the environment, right? You can be very, very precise, but then if it kind of broadens up, so there is a relation between, there is a limit to what point actually you can go. Yes, you're right. But that's a good solution, for example, for millimeter wave, right? Here you see why it's important. If you really have to be, you don't have to squander power in millimeter wave, that's a possible solution. That's why from the beginning of the 5G story, millimeter wave and massive MIMO were kind of coupled, okay? Massive MIMO has other applications without millimeter wave and vice versa, but definitely their combination makes sense. Okay, uplink and downlink have different problems. So in uplink, there is the problem of contamination, as I mentioned briefly before. So you do have to estimate the channel. Each user will get a pilot sequence, and you need at least as many pilot sequences as users in each cell. Now, due to coherence time, you have to reuse the pilots because you can't really coordinate too large an area. So you start to have problems with collisions, right, with interference, because some users are reusing the same pilot. You have a finite set of pilots, and because of time coherence, you cannot coordinate everybody. Also because in that case, you would need a larger amount of pilots, right? And that takes time, effort, right? So they reach kind of a compromise. They say, okay, we are happy enough with the different cells. We want orthogonality within the cell. We are happy enough with the non-orthogonality between cells, but of course then you give rise to pilot contamination. This interference is basically an error you commit systematically when you estimate the channel. Yes? There are solutions. Okay, so one solution is to coordinate the to have some form of I mean, you can't coordinate centrally, but we could start to have distributed solutions. So we try to apply game theory for this, for example. So it's like a game, you know, and you try to do what's best for the system, kind of, okay? You might have some limited form of coordination. For example, where this will hurt, it's probably at the boundary, because the users at the cell edge are already in trouble because they have a low power. So their estimate is already shaky. If you add interference, very big problem. So you might think of some coordination at the boundary of the cells. Not everybody, not all the users, but maybe for those you have to be careful. Yes? It's like reuse. They have this soft frequency reuse thing, right? Where you reuse things at the cell edge. It's similar to it. Now, in the downlink, you actually have a bit less problems because of the way you form the beams in a very precise way and so on. If you play with the law of large numbers, you become orthogonal between base stations, so they do not interfere with each other, essentially. The assumption we make here is that the environment is not insanely mobile because they use TDD to do the feedback. Bit. They don't do feedback basically, so they use channel reciprocity. So if the channel doesn't change, you know, sensibly between downlink and uplink, you can essentially just avoid the feedback, right? You just assume that what you see when you receive in terms of channel is what you see when you transmit. Now, if there is mobility and the environment changes, then this is a shaky assumption. So that might need some other work. The problem with FDD is also it needs more pilots. Hardware is more heavy. Time division techniques in general, same with access and so on, they're easy because they do not imply really hardware problems. What do? You use the system, you don't, right? Powering up, that's what TD things are, right? FD, SD, CD, they are all about something smarter, right? You have to do some, you have to use some techniques. You have to use some filters, some codes, some signal processing. TD is the easiest thing you can do. Of course, you eat up the delay budget, yes? And in this case, you might be at, you might clash with the mobility part. If you want a very mobile system, TD is not a good idea, yes? If you want a very responsive system, TD is not a good idea. So it depends on what you need, right? What are the benefits? Well, as we said, because of the large number of antennas, paradoxically, you are simplifying multi-user processing. You can get away with linear things that approach actually Shannon limits, okay? Without doing strange things at transmitter and receiver, without maximum likelihood, without dirty paper coding. You're getting there, you're close to that. You reduce the transmit power because you're much more efficient, right? You have a better beamforming, therefore you're more efficient with the power. The noise and the fast fading vanish because of the averaging due to the fact that you have so many antennas. It's like what they call channel hardening, right? In spatial diversity. It's to the extreme though. You have hundreds of antennas. Now, you are using TDD, which is an immediate red flag for standards. So far, cellular systems have always been about FDD. Now we come and we say, okay, massive MIMO is great, but you have to change the duplexing. Maybe not, right? So you see that that's why you have to be a bit careful with these more radical innovations, right? And you do have pilot contamination. That is part of the game. Of course, there are solutions, but it's something you don't have for traditional MIMO. I'm not sure I want to spend too much time on this table, but it's kind of a summary. So they kind of tell you a comparison, which is visual also, between multi-user MIMO and massive MIMO. So you see, okay, so we already discussed TDD. The channel quality changes quite a bit in multi-user MIMO. So you actually have a channel that where the small scale fading plays a role. That's not really the case in massive MIMO, which is good and is bad, because the diversity could also be used to your advantage. If you have a channel that varies, you can have multi-user diversity, right? You can have a channel of the user A that doesn't look like the channel of the user B. Therefore, you can play with scheduling over time. It's an additional degree of freedom. That's gone with massive MIMO. On the other hand, though, you are saying that you don't care even about that because they all coexist. You have already your orthogonalization process because of the many antennas. You have these channel vectors that become orthogonal to each other in the long, you know, as number of antennas increases. So you don't care. They can all even be very, very close. You can be super precise with your beam. Why do I care about scheduling? Maybe scheduling is gone altogether. So you see there are complications in terms of RF and so on, and you know other things like the duplexing has to change. But on the other hand, they tend to lead to a very simple MAC. So as a byproduct of massive MIMO, you probably are not so concerned about things like spectrum sharing, even MAC altogether. Okay, this is open for debate, but it seems that it's less of a problem than it used to be with massive MIMO. Yeah, so again, I think, I mean, my impression is that massive MIMO is more for systems that are kind of settled, fixed positions, you know, that is very good. I think you could totally think of massive MIMO as an alternative to backhaul if you cannot deploy fiber. You have two panels, you know, maybe even a few kilometers far apart, line of sight, you really stream a lot of data, okay? Or for things where you need to be very precise identifying something, okay? That's localization things. I think they have a very good, there is a very good potential here. Extreme energy efficiency, okay, and stuff like that. And another good thing is that you can actually complicate as much as you want the infrastructure without touching the device. So to some extent, you can even picture massive MIMO for IoT. I mean, to some extent, because they are not going to require really the guy to do much. One antenna, linear signal processing. So good deal. Okay, you move all the complications to the infrastructure in a sense. Okay.
What is the channel reciprocity?
It basically means that the channel you have in downlink is similar or same as the channel you have in uplink. Okay, if that's the case, you talk about channel reciprocity. So the link you have from base station to UE is the same, and that's normally the case where you don't have time variations, right, in the system. So you don't have really Doppler spread playing a role, for example. You don't have things moving around.
Channel characteristics are similar.
It's probably the same, actually. Could be even the same, right? If nothing changed, of course, maybe there are small changes. So up to some point, largely speaking, is the same. And then they do not need a feedback channel, right? Because if the channel is the same, I just listen to it in uplink, say, and then I assume in downlink is the same. So you get rid of all the feedback problem, yeah? But that requires assumptions of kind of static, not so variable environment, yes? And that's what they assume with massive MIMO, okay? Which is a good thing anyway to get rid of feedback channel, because here you have to kind of, the channel information is about hundreds of antennas. So it's good to have a cheap way to acquire channel information, right? You don't need to design, and you would need to waste quite a lot of bandwidth if you were doing FDD approach to feedback, right? So it's a good thing actually that you can use channel reciprocity. So the way we are going to talk a bit more about the technicality in the paper club, but essentially what you do, the UE sends a signal as it normally does for estimation, and then the receive antennas do the job. So the user is not really doing anything here. Okay, so easy. And the channel vector up to infinity in terms of the number of antennas can be learned from a single pilot transmission. So it's as difficult for the user to estimate one link as it is an infinite amount, because it sends the same thing, right? The job is done at the receive array, okay? That's good, again, to keep the thing simple on the user side. The base station does a similar thing, and again, the UE doesn't have to do too much. So you have this. So you have to, of course, agree on the pilot, but again, you do not have to. So you do not have to do too much work. Okay. So this is basically, you would have to collect all the estimates of the channel vector at the UE, and then you basically use reciprocity. Okay, so what you have is here M pilot transmissions, because you need to send one pilot for each of the antennas. Okay, but in general, if you compare this with FDD approach, this is way cheaper in terms of number of pilots. Okay, we're going to discuss this better in the afternoon.
So this estimate is going on in the receiver end, right?
Yes. So yes, this is downlink. So basically, you are.
Yeah, both should work for the CSSST.
Yeah. So yeah, so definitely it's less work to. It's kind of similar, right? Because you have, in this case, you have again, you have K, right? And then, but the pilots are just one per user here, right? Here the pilots are one per antenna, right? And the pilot set is handled by the base station. So again, it's not a big ask to the user, yeah. Okay. Okay, we'll have more about this, definitely more about these problems in the afternoon, so I'm going to go forth. Now, it's important to understand what coherence is, okay, because that's what tells you information about the channel. If you are within a coherence block, so within a coherence time or coherence bandwidth, you don't need to do more than one sample there, to take more than one sample, because they're all the same kind of, right? So what you have is that, let's say your coherence bandwidth is BC, okay, and the coherence time is TC, then what you have is that each coherence block would cover BC times TC complex values samples, okay? The typical values of coherence time and coherence bandwidth vary in like very broad ranges, okay? So you have from 1 to 50 millisecond coherence time depending on the environment, if you are indoor or outdoor, for example, and coherence bandwidth as well. So you have between 200 kilohertz and 1 megahertz, again depending on the environment, mostly to do, well, coherence time actually is mostly to do with mobility, and coherence bandwidth is mostly to do with the multipath, you see, the physicality of the environment. And so with these values, you can actually have coherence blocks that are very tiny. It means you have to feedback, you have to sample more information about the channel, or you have very large coherence blocks. These you have to sample less because the environment is more static over time and frequency, yeah? And you can actually think of different ways to assign coherence blocks. So you can play with frequency or time, okay? And there is the way also you, well, that depends also on the assumption whether you have TDD or FDD, okay? But essentially, the number of samples in a coherence block would tell you how much effort you have to do when estimating the channel.
So instead of a coherence bandwidth and time, coherence bandwidth is related with the mobility of the.
No, that's the other way around. So time, coherence time. So the faster the nodes move, the shorter will be the coherence time. Yeah, and the more actually the coherence bandwidth has to do with the delay spread, which is a consequence of the multipath. So if you have more multipath, you will have a higher delay spread, which means a lower coherence bandwidth. Yes. Okay, we are going to see more about this in the afternoon, but essentially you can have a measure of how many pilots you would need if you were applying TDD and FDD, okay? So in TDD you need essentially K pilots, okay? In FDD you need M plus K over 2. So definitely there is a big gap because M is normally much greater than K, right? So if you go through the steps, you see, okay, why they came up with this number. So that's one of the main reasons why TDD is actually favored, okay? It's simpler. But it implies that you have to have a coherence time that suits you, okay? So what are the final observations about massive MIMO? Okay, we can say. So pilot contamination is a deal, big deal maybe, but you can possibly use coordination between base stations to cope with it, okay? Channel aging effects are of the essence because, so channel aging means basically how quickly the channel decorrelates. If the channel decorrelates quicker, then you can less and less rely on the assumption of TDD. That's why some people are working on FDD. FDD, by the way, would be welcome news because that's how cellular networks work. So if you could have a massive MIMO version, practical massive MIMO version working for FDD would be very good for the standard integration, I think. I'm not too sure there has been too much progress on that though. It's still mostly TDD in my opinion. There is a problem. We don't really know how to pack so many antennas in a base station yet, okay? Especially for millimeter wave, the question is open. Yeah, massive MIMO is a part of the cake. It's not the whole cake, so it will be an ingredient, okay? But there are other things you can do. So for example, you are talking about energy efficiency, but you could as well play with MAC and start to switch off nodes if they are not needed. So there are always multiple ways to get the same thing, right? Throughput, yes, but throughput you could over-densify the network. So you see, Massive MIMO is an option, it's not the only option, right? Yeah, and as I said, millimeter wave is coming up strongly, so you do have this meaningful combination of the two technologies, millimeter wave and massive MIMO. Yeah, I was asked about the bands before. Here you see a list, yeah. And basically, you do have two approaches that go hand in hand. So millimeter wave needs to be you need to be very directional, right, and high throughput, and massive MIMO gives you that. So that's why they are thinking to combine them. You can have really a lot of antennas in a small scale, hypothetically. It's a meaningful combination of millimeter wave and massive MIMO again, because of course the spacing between antennas is proportional to the wavelength, which is inversely proportional to the frequency. So the higher you go, the more you can space antennas. But a rule of thumb from RF engineering is that the higher you go, the messier it gets. It's more expensive, more difficult to do proper RF engineering design at higher frequencies, right? It's more difficult. Larger bandwidth doesn't necessarily mean better deal. So in millimeter wave, you have a larger bandwidth, but then you also have a higher power of the noise, right? In the Shannon equation, bandwidth appear in two places. Before the logarithm, which is good because it multiplies things, but it also appears at the denominator of the SNR or SINR inside the logarithm, which is bad because it brings down the thing, all right? And in fact, you can show there is a hard limit. It's a constant. If you go to infinity with the bandwidth, you are not going to benefit anymore in terms of capacity. Yeah, you can find this as a basic exercise in some wireless books. Power is different. If you are isolated and you have the circuitry and you don't disturb anybody with interference, the limit of the capacity with power is infinity. You can go as much high as you want, theoretically, of course. Then you have interference, circuitry, power amplifiers, but theoretically you can benefit from power all the time. From bandwidth is not true because of the noise. So millimeter wave is in the realm where you have a lot of spectrum, and that's not necessarily always good, right? And you, on top of it, you are collecting actually, I think the fact that you have such large bandwidths means very complicated signal processing in terms of the samples you have to process, probably the energy you are collecting over such a broad spectrum. So there are some challenges still to be solved besides massive MIMO. If you have the right configuration, though there are these problems with channel being unreliable and so on, but if you have the right beamforming, maybe mobility is not an issue, maybe you're indoor, maybe not too many obstacles, then probably it's a good solution. Okay, so hardware can leverage insights from a lot of work that has been done before. You have these 802.11 standards, right, that work with actually millimeter wave already. Yeah, but you have issues with mobility, directionality, right, and so on. We are not independent in terms of spectrum availability. We have to rely on what the regulators tell us, so we have to see also what happens in that space, right? And there are a few bands, many bands that could be used, but it depends on what becomes available. Most likely it will coexist with microwave cellular systems. It's similar to the story of small cells and macro. This is not going to provide coverage. This is not going to be used for control plane. It's definitely a case where you use it for data plane and localized transmission of information. Other applications, by the way, you see, mobility is a relative thing. It depends mobility with respect to what. If you have two fast-moving cars and they communicate with each other, if they don't change position relative to each other, that's a static environment as far as we are concerned. So you could use millimeter wave there, and you could have applications for high throughput, for example, for safety or entertainment. You can think of exchanging a lot of information between cars that are moving, okay? But it's important that the relative movement is not there. That's what matters, right? Yeah, and of course backhaul. We did backhaul a millimeter wave for a while, so that's going to stay. Okay. So in conclusion, for about this MIMO, small unit of the core. So cooperative MIMO will be used somehow. You need actually better infrastructure though, and you have to be mindful of overheads. We saw the terrible efficiency of these systems, right, in terms of radio over fiber and so on. Massive MIMO, of course, it's about the mobile broadband story also, right? It's about boosting the data rate. You need a lot of antennas. Possibly you could use cooperation. You could have multi-massive MIMO. That's not really there at the moment, but you could have a combination of the first two categories, right? You could have virtual massive MIMO enabled arrays. You could do that, yeah? So that's get crazy. And then you have millimeter wave MIMO, which is actually a bit more on the side of localized transmission, right? Local applications. Potentially very high throughput can be achieved. Hardware challenges are there. And you might have to do more radical system changes in the design, okay? So massive MIMO is more backward compatible in a sense. If you exclude the duplexing bit, which is kind of big, millimeter wave seems to me a bit further. So in fact, somebody talks about early 5G and more mature 5G, distinguishing whether they use millimeter wave or not. Okay, so you might have first releases that are not about millimeter wave actually. Okay, hope it makes sense. So I give you time to go to the bus and to have lunch. So we'll meet at 4:30, I think. Oops. For the tutorial. Yeah.
Are we going to discuss the first paper that you have shared?
Yes. Yes.